All right, let's take a look at another indirect proof, or another proof by contradiction. And now I know that this proof was written down as an example, but I think so many of us probably are going to want to talk through these types of proofs. I figured a video might help just to kind of clear the air a little bit. So we are asked to prove that there is no largest prime number. Now, another reason why I feel the need to go through this is that this is a proof that I feel like you really should have down. This is sort of like a feather in your cap for any mathematician should know how to prove that there are infinitely many prime numbers and that there is no largest prime number. And so this proof actually stems way back to the Greeks and was written down by Euclid himself, who is often referred to as our father of geometry. But let's give this one a shot and see if we can understand it. So if we're to prove that there is no largest prime, let's assume that we know who that largest prime is. So obviously our first prime number is 2, our second prime number is 3, our third prime number would be 5, and so on and so forth. Let's assume that there is some capital P that is the largest prime number. Now, I'm not saying I know what it is, and actually I think we all know that there isn't one, but we're just going to make this our assumption. So let's assume that capital P is our largest prime. Now, that said, let's continue to think about numbers for a second. Let's say I give you a number that is created by taking 2 times 3 times 5 times each of the primes until we get to P, and then you know what? Let's just add 1 to it. So n is going to be a number that is clearly bigger than P. Now, why is n bigger than P? N has to be bigger than P, and the reason is that we know that n has P held inside of it as far as one of its a number that generates that size, and we've then added 1 to it. So we know that n has got to be bigger than P. But then let's take a look and see if we can understand why this this sort of leads to a contradiction. So we know that n is at least as big as P plus 1, and we know that it's definitely larger than P. So we know it cannot be prime. N is not prime. And the reason why it's not prime is because we assumed that P was our largest prime due to P being largest. So that must mean, therefore, that n must be composite. Now, if it's composite, what that means is that it must be divisible by any of the prime numbers that we have, by one, at least one of the prime numbers that we have, 2 leading all the way up to P. Now, let's go ahead and begin to take a look at this. If I take the number n and I divide it by 2, I get some number, but then I'm going to get some number with a remainder 1. If I take n and I divide it by 3, I'm going to get some number, but then I'm going to get a remainder 1. And why am I always getting a remainder 1? Well, that's because I added 1 here at the end. So the reason why this is problematic is that n has no prime factors. We could even take and try and divide n, we could even try and take and divide n by P, and what we're going to get is we're going to get some number, but then we're going to get a remainder of 1. So it's not a factor of n, which means, therefore, that n must be prime. Now, the fact that we just said that is our contradiction. That is where our two arrows are sort of pressing against each other and saying, how can both of these things be true? We have n being prime, we have n not being prime. How can they both be true? Well, they can't. So what do we attribute this to? Well, we attribute it to our very first assumption. We assumed that P was the largest prime. And what that means is, therefore, there does not exist a largest prime. I hope that helped.